but physically it can be separated by the block. So we have blocks. So block is the number of the basic unit of the ion. So eventually we will count the number of blocks. Okay, when the DB engine search the data, how long it takes. So how can we measure? Sometimes I can say the disk query is fast, slow. How do you measure the performance of your query? Are you going to use your watch or the stopwatch or wall clock? No, we are going to consider number of IU. Why? There are a bunch of other resources that are required to measure your query. So CPU, memory, but the number of IO is the most expensive one. It's the dominant resources. Okay, so we can ignore the CPU resource. We can ignore memory resource. Instead, we are going to measure how many IO are required to access the data. Okay, input and output. Because accessing secondary storage is the most expensive operation. Expensive means takes a longer time than other. Okay, so this is a block, this is a block, so this is a block. What is the naive way to access the data table? So this is a student table. So what is the naive way to access such a data? So I'd like to find the lead. One by one. You can read each block linearly. That's called a linear search. Sometimes it's called sequential search, or sometimes it's called full table scan, depending on which DBMS you use. So each vendor use different, but concept is the same. You can search one by one. Okay. So for example, so if you have the P number of block, so complexity is B over 2. Why? If you are lucky, you can get the data from the first IO. Otherwise, it will take B number of IO to access the data. So overall, average is B over 2. B means number of IO. So this is a full table scan for linear search. So when we have a huge number of the blocks in your table, so this is the number of blocks and this is the time. So it's a linear increase. So we want to speed up such a thing. How? Using the index. Index is another data structure. It's typically located as you can see the index from the textbook. Index is a part of your group. It's physically located. It's the same thing. In addition to the table, we can build the indexing structure depending on the data structure of your table. Data file structure. Okay? So the primary index is used for what? In case your table is sorted by the key value. Okay? Eventually we will put such a key value as the primary key. Okay, we can then get the benefit of this one. That means we can get the anchor, 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 anchor. Then build the index. This is one index consists of a number of blocks. Okay, same idea of the blocking used in the table. Okay, so this is the primary index. It's a non-dense index because we don't need all of the record. Instead, we need one record that represents each block. Okay. So also, now what about the column that this table is sorted by the non-key column? For example, department number in employee table, student table. So 111 is sort. That index, so such a column, that is a clustering index. It's a still non-dense index. Okay? Why? We don't need all column 1, 1, 1, 1, 1. No, we don't have to index all of that. Instead, just a 1. Okay? That represents that group. So that is a clustering index. Also, we can build the index. So primary key is the most important, the column in the table. Why? using primary key, you can find specific data row. That's the definition of the primary key. So non-null and unique. Because of uniqueness, you can find easily the data. Also, it's non-null. So all data entry, all data, all tuple has one, the primary key value. So, however, sometimes we want to access the data which is not primary key. That's usually happens. Okay? For example, I'd like to access the data by the age. Sometimes the same age, sometimes not. It's a duplicate data. So we can build the index for that column that is called the secondary key. Okay. In case that is the key, which means it's a unique. What is the example of such a secondary index with the key attribute? Candidate key. Okay. For example, employee. Employee has candidate key for employee ID and social security number. Both of them are key. Okay, we have two key, candidate key. We select one of them as a primary key, the other will be secondary key. In that case, we can build an index for that. Even though that's unique, that's not selected as a primary key, but we can build an index. At the time, it's a dense index because it's not ordered by that key. So this is ordered by employee ID, but not for a social security number. So you'd like to build an index for social security number. At the time you need all of them because we cannot guarantee they are sorted, right? So that is the secondary key, the secondary index for key column. Non-key column, sometimes it can be dense index, sometimes a non-dense index. So we can build a secondary. So this is a single level index. What if this one is, before that, how can we search the data using? First, you need to find the index, okay? How can you find that? Using binary search, cardinal hop, and see. Oh, first hop or second hop? Cardinal hop, cardinal hop. Because they are already sorted. That is the nature of index. It's already sorted. Then access the data, and finally we can go to the block. Then inside the block we can find the data that you want. How can you find the data inside the one block? Binary search. But we do not consider the time, searching time within a block. Why? Even though we use linear search, even though we use the binary search, it's short amount of time because it's in the memory. Okay? Almost we can ignore that amount of time, so it's just one. Okay? So for example, you access this one, you access this one, finally you get the data 1, 2. 2 IOs are required. Sometimes 1, 2, 3. So 3 IOs are required, which means longer time than 2. Then you can measure which query is faster. Then, what if this index is so big, so you have 1 million of index block? Even though you use binary search, it will take log n. 1 million is 2 to the power of what? So 10 times, whatever, 12? So million is 12. Anyway, it takes a lot of time. So the more, because log n is graph like that, the more data you have, the longer time it takes. Okay? Even though that is not linear, but it takes a longer time. So to solve that problem, you can make the index of index. Also index of index. Okay? Eventually we can build such a tree structure. This is called search tree. How can you use the search tree to find the data, to access data? What does that mean? This one. It's a node, right? According to the algorithm course that you already took, right? You already took the algorithm course, you learned tree structure. Tree means it's data structure. And also you learned the similar thing, graph structure. What's the main difference? Graph versus tree. Which one is the superset. Which one is the general structure? Graph. Both of them has graph and edges. But tree has parents and children relationship. It's always top to bottom. Okay? It has the root node and leaf node or terminal node and internal node. So we are going to use such a search tree. So each node represents block. Okay? Each node represents a block. So what does it mean? So this children node. It's the next level index. For example, we have 1, 2, 3, 4, 10, 20, 30 for employee ID. Less than 10 goes to here, which means we have 1, 2, 3. And bigger than 10, less than 20 goes to here, which means 11, 12, 13. And bigger than 20, less than 30, 21, 22 goes to here. Okay? This one, 11, less than 11, 10. 10 is already 10.5. Okay? Just like that. So less than this value goes to here, bigger than this value goes to here, between, something like that. It's a very simple structure. It's a tree structure. So you can search the, so I'd like to access the data 10.2. So 10.2 is bigger than 10, less than 20 goes to this children node, and less than 11 goes to here. Finally, you can find the data. What does that mean? It's an index entry. Index entry has the key value plus 1. Page number. Pointer. Address. Of what? Point of what? Why do you need the index? You want to search the data in the table. So, in address of table node, not table blocks. Okay? Then finally, you can access the data. Employee 10.2. 10.2 is here, lead, and address is 57,000, right? Just like that. Okay? This is the search tree, multi-level index. And also, the benefit of this search tree is it's a dynamically changing. So I have new data like the 10.55. 10.55 is belongs to this node and this node, and if you have a space in this node, you can put it. Otherwise, you can create the children node. If the node is full, node is a data structure. Okay, node is one data structure. So, for example, we can keep the 3 index entries in one node. At that time, it's called the P order P equal 3. So we can keep the 3 index entry. Just like this one. Blocking EL was blocking factor. What does that mean, blocking factor? How many data in one node? How many index entry in one node? How many index entry in one node? 3. So you can put the 3 index entry in this node. The difference between this one and data node is this one will be used for distribution of the children node. So you have another pointer, that point children node. Who will see details about this indexing node structure next slide. Before that, so this is called the dynamic search tree. It can be dynamically increased. Also, it can be, if we delete the data, you can dynamically. It's not very difficult. You can build it by yourself. You already built the search tree structure in your algorithm course. If you do not remember, probably you did link this, right? And something, data structure. This is one of the database, just improving that idea of the algorithm, data structure that you learn in the algorithm course using search trees. So it's good, it's easy to understand and easy to implement. You can implement it right now. If I ask you, so why don't you build a dynamic search tree? You can do that, okay? I think that it takes 10 minutes, 15 minutes. Probably you can do it. Then, no, 10 minutes is not enough? Okay, 20 minutes. The problem of the search tree is what? I probably mentioned at the end of the last class. Time consuming doesn't take a long time to access the data.
Has linear complexity, but it depends.
It's not linear complexity. It's hard to measure the complexity. In other words, for example, the data is the index entry is located in this node. How many I/O do you need to access the data? 1, 2, 3, 4, 5, plus 1 data. So total 6 I/O to access the data. What about this node? We have data 1, 2, 3, and 4. What about this one? 10. 1, 2. Sometimes 2, sometimes 5, sometimes 6. It's not guaranteed. In other words, so I gave you the example of traveling from here to Manhattan. So which one is the fastest way? Drive 100 miles per hour through I-95. It will take just 30 minutes, 40 minutes. You need to pay the ticket. Right? But anyway, if you drive in the morning, 6:30, 7 a.m., definitely you will be stopped. The exit 27. Right? Because of traffic. And also, who knows? There is an accident. So if the highway is blocked, it will take 3 hours, 4 hours. So you cannot guarantee. So I would recommend to use train. Train usually, so 1.5 hours, plus minus 5 minutes better. So it's guaranteed, even though average arrival time is slower than the driving, but we can guarantee the time. We can easily plan for your travel. Same thing in the query processor, DB engine. So DB engine allows such a guaranteed time to schedule your query. Okay, at that time, dynamic search tree index is easy to implement and dynamically change it, but we cannot guarantee. Sometimes it can be skewed like that. Skewed tree. Okay, so we are not going to use this one for real productive the index tree structure. We need to solve that problem. This is unbalanced, so we need balanced tree structure that is called B-tree indexing structure. Probably some of you guys already heard about the B-tree structure or B+3 structure in the magazine or the job interview or your work experience. Many of you guys are thinking B means binary, right? Yes.
What is the difference between B and matrix?
Who is? Okay. Okay. So this is a balanced tree structure, which means what is the balanced tree? All leaf node. What is a leaf node? Terminal node. Who does not have children? Node. So this one, this one, this one. So this is a leaf node, terminal node. How many depths? 1, 2, 3. Level. 1, 2, 3, 1, 2, 3. So at that time we can say this is a balanced tree. Okay? We want to make such an indexing structure. How can you make that? Any idea?
Rearranging the tree and change the roots.
Okay. Then how? How to change?
We separate the table. We separate the table.
Separate table what?
We separate the
Separate the table. Separate the node.
Yeah.
Not table. Table is here.
Yeah.
Okay. No. How can you separate? The problem, why we get the skewed branch? Why? It goes from top to bottom. Okay, we don't know where your children go, right? If you let your children play, and so he or she will go anywhere. So why don't we build a tree structure from bottom to top? Okay, how many root nodes do you have? Only one in the tree structure, right? So if we can build the tree structure from the leaf node to top, then all leaf nodes may have the same depth, same height, same level. So balance. Don't you think that works? Yes. So that is the way, basic concept of how to build B3 index, balanced tree index. Think about the search tree. Search tree actually starts from the top, right? And if that is full, split. Sometimes think about the root of your plant. Like you have a bunch of root this side. We are going to do the opposite way, from bottom to top. Then all leaf nodes will have the same depth. So that's the idea of the building B3 index. We will see. You can. So this is a search tree. So do not forget what is the structure. What is the index? Index is nothing but data structure. Okay? When you are doing the programming, so you probably define index integer I, right? Integer j. What does it mean? Integer I, integer j. Integer is data structure. That's different from floating, or decimal, or the just number. Each data type has their own data structure. Index is another, little bit more complex. The data structure to keep the data. Okay? So this is one index, each one has the node. They are connected, parent and children relationship. That is the indexing structure that I already mentioned. Okay? So each node has, as I show you here, each node has set of pointer and set of key value to represent the pointer of children and the key index key value. For example, like this one. This is one node. Okay? At this time, how many children are possible in this node? How many children? 1, 2, 3, 4, 5, 6. I and go on total Q number of children are possible. How can we determine? Depending on blocking factor. Okay? Depending on the size of your key, it can be variance. But you need to define how many. What is the Q value in your one indexing structure? So at the time, Q is called order. Okay? Order of this index. So this node has the Q number of how many key entry? Index key entry in this node. So this is the pointer. Then 1, 2, 3, 4, I minus 1 I and go on Q minus 1 key value. For example, so in case Q equal 3, so pointer, and 10, 20. You can have two index value. Actually, key entry has the key value plus what? Data pointer. This is the pointer for what? Go on, and this pointer, this one. Okay? And this is point 20, go on, and this. You understand? So this is just the diagram to make you understand the data structure of the search tree node. Then, this is the pointer of what? Children node. Children node should have the same data structure. Like this one. This one has the same. This one has the same. And then pointer, 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 pointer of this children node. But this time it's a null pointer. Why? They do not marry yet. They do not have any children. Right? It's a null pointer. Okay? So this is not null pointer, this is a point to this one. It's the address of this. Address of this block. This is the address of this block. What is the condition? Less than 10 goes to this one. Bigger than 10, less than 20 goes to this second child. And bigger than 20 goes to third child. Yeah, for example, 2, 3, 11, 15, and 23, and 30. Like this. When you insert the new data, like the 100, where it goes? 100 is bigger than 20, so definitely the third child. Okay? But there's no space. You can grow. Dynamic grow. So how can you grow? You can have 100. Then point. This one. Dynamically grow. It's just simple. Wait. 101, 101. 102, 102. Same. Because of that, it's skewed. It's unbalanced. Okay? So this is a search tree. How can we search the data? Just follow the same way. I try to search 30. Data. Employee ID 30. 30 is over here. So block number 5. 30 is bigger than 20. So goes to here. And 30 is here. So you don't have to go deep inside. Instead, get the pointer of data. Data pointer. Where's the data pointer? This is go to block number 5. How many IOs do you need? 1, 2, plus 1 more data. Then you can get the data. Index ID 30. Okay, this is a search tree. However, as you can see, will grow skewed. So we try to make the balanced tree. That is called the B2 index or B plus 3 index. Idea is, instead of building index search tree, the top to bottom, we try to build bottom to top. There are conditions. So we are going to use the same node structure, which means in case Q, order Q is 3, we will build like this is a node structure. It's the same as the search tree. Okay? How many children node? Children pointer. How many children each node can have? In this case. How many children? 1. This is a pointer. Children node pointer. This is a children node pointer. This is a children node pointer. How many? 3. It's the same as number of order. And how many index key entries? Always -1. It should be in between. 1, 2. In this case, 2 index key entries are possible. In case Q equal 5, you can make the node structure 1, 2, 3, 4, 5. Children pointer and data pointer. 3, 4. K1, K2, K3, K4. All node indexing structure has the same thing. Then, this is important. you can insert the data into this index key entry. For example, 1, 2. This is the index key value. What if when you insert the 3? Is there any space? No. So, in case of search tree, we can just grow this way, right? Instead, we are going to do opposite way. This is called full condition. When a node is full, okay? When node is full, which means no more space for index key entry, then you need split into 2 nodes. Okay? How can we split? Just copy. Copy the node. So this in this case. Copy. Then how? So first the split, then we can divide into 2, right? So how many data right now we have? 1, 2, 3. We have 3 index keys, right? So decide the middle value. Find the middle value. Which one is the middle one? 2. Then 2 will be, middle value will be promoted. Promotion means it's going to up patterns. So copy. So this middle value goes to parent node 2. And less than middle value, this one going to left hand side. So 1. And bigger than middle value, right hand side, going to right hand side. Okay? Then next is pointer. Less than 2 goes to here, bigger than 2 goes to here. It's growing up, bottom to up. Unlike the search tree, it's grow bottom to up. How many? Yes. 1, 2, 1, 2. It's balanced. So this is called B3 index, balanced tree index. How can we build? First, build the node structure. Okay? Based on the queue order. Okay? Then you can insert the index key entry until full. In case of full, we split into 2. Split means make the club, copy. Next. Okay? Then find the middle value. Middle value will be promoted. It's called a promotion. Become pattern. Okay? Then, what is the node structure of the pattern? It's the same thing. Always the same. Okay? Then, less than middle value goes to here. Bigger than middle value goes to here. Okay? That's it. That's the B3 index. Very simple. And there might be a question. What if Q is equal to 4? Which means we have 1 more. Right? So we have 1 more. So for example, you can keep 1, 2, 3, but when you have 4 data, it will be full. So we have even number. What is the middle value in this case? It's not median, it's a middle value. We cannot make them average. Right? This time it can be either 2 or 3, depending on DBMS. Some of the DBMS is left hand side, some of the DBMS right hand side. In our class, we will select this one, cut in half, and left hand side as the middle value. Okay? Depending on the textbook, some of the textbook use this one as the middle value, but in our class, we will use this as the true. So always, when you determine the middle value, you will need to select this one as the middle value, then 4 motive. Okay? So in this case, 1, 3, 4, and 2 will be 4 motive. Some of the DBMS, some of the index use this one, doesn't matter as long as you keep the consistency. But in my class, in our class, we will use this one for consistency. Okay? So let's take a look at the example. Okay? So first, this is a node structure in general case. Okay? In this case, Q. How many children pointer? Children, Q number of children. Okay? Which means we can build this one, this one, this one, this one. Then, how many index key entry for each node? 1, 2, 3, 4, 5, 6, up to Q minus 1. Always minus 1 because it should be in between. We are not going to put the index key entry after times the children pointer. Okay, so let's take a look at the example. I know, I think the only few students understand right now about the B3 index. But if you take a look at carefully the example, you probably can understand. Okay. So let's use this part. So we are going to insert 8, 5, 1, 7, 12, 9, 6. What does it mean? So I know some of you guys already got confused. What does it mean? 8, 5, 1. Actually, we try to insert the data. A, Lee, and tower view, and CS major. This is one tuple, one row. Okay? This is a primary key. And next, 5. The Parterre, and University Avenue, and E. Next, 1. Okay? James, and University Avenue, and Mechanical Engineering, and so on. But we try to simplify because we try to build indexing structure. Okay? For this data table, student table. So I simplify the data by picking up only index value, primary key value. That is 8, 5, 1, 7, 12, 9, 6. We try to insert this data in this order. Okay? Then we want to build B3 index. To build the B3 index, what do you want to know first? What's the node structure? So at this time, Q equal to 3. Order Q. So sometimes it's called a P. P order, the order is 3. What does it mean 3? How many children pointer? 3. How many index key pointer? 2. So that means first you need to construct node structure. So node structure 1, 2, 3. Okay. Then index key. This pointer and this pointer are different. This one is pointer for what? Children node. This one is the pointer for data node. Eventually, you want to know this pointer to access the data. Okay? So this is the node structure for this example. Then we will start. First, insert A. Inserting A means actually entire row. But we simplify the problem. We do not have any data yet, so we need to create the node first. Node always the same as this one. all of them are null pointer. Then where's the first? A. A. So A probably somewhere here, right? Data block. So for example, this is the block number 5. So block number 5. So we can point this one. But I ignore in this example. It's too complicated to understand if I point to the data pointer. So data pointer will be eliminated here, but there it is data pointer. So I will use solid circle to represent there it is data pointer. What about the next one? 5. Okay? So 5, do you have space in this node? Yes, we have the empty key entry 5. In this case, even though it doesn't take a time to search the data in the same node, we do better sort the data, making the order automatically. So 5 and 8. But it doesn't matter. Right? Eventually, it's a matter of the children node. Right? When you construct the children node, you need to order the key index key entry. So 5 and 8. Then we have data pointer. No children pointer yet. So we need this one. What is the next? 1. So we need to insert the 1. Do you have space? No. It's called full. It's a full situation. What happens in case of full? We need to split. Okay? So split means copy. Make the clone of this. We need to rearrange this. We have 1, 2, 5, 8. What is the next? Find the middle value. Which one is the middle value? 5. Obvious. And 5 will be promoted. It's a promotion. Do you have the parent node of this one? No. So which means we need to create parent node. Same data structure as this one. Exactly same thing. Okay? Then 5 goes to here. Left hand side? Left hand side. Right hand side? Right hand side. Then data pointer, data pointer. That's it? Not yet. You need to finalize children pointer using L. That's it. Is it balanced? Yes, it's a balance. 1, 2, 1, 2, same level. Then we did this. What about 7? Next. 7 is bigger than 5. So going to here? No. We need to find the leaf node as low as possible. Okay? So which means going to this children node. Is there any space?
Yes.
Yes, there's a space. So we can put the 7 over here. So we can sort the data 7 and 8. And this. Okay. Next 12. 12. Where it goes? This one, A, B, C. Which node?
C.
A,
Yeah.
B. Definitely B is not. C. Even though there is a space over here, we do not insert the 12 in this node. Always we need to find leaf node 1. Bottom up approach. Okay, we are going to start from the bottom always. Even though there is a space, there is a room for next value, we are not going to use this one. So 12 is bigger than 5, so it's supposed to be here. Do we have space? No, it's called a full. In case of full, we need to do split. Copy this one. And 7, 8, 12. Which one is the middle value? 8 is the obvious. So 8 will be promoted, going to parent. So it's the same thing. Insert 8. Do we have space?
Yes.
Yes, we have space. So 5, 8. Then left hand side 7. Right hand side 12. That's it? Not yet. We need to finalize. Then it's done. Is it still balanced? Yes, it's balanced. 1, 2, 1, 2, 1, 2. So how can you search the data pointer? Data 12. 12 is bigger than 8. Going to this one, 12 is here. So probably this one is a pointer of data. But we will simply find the problem. We will ignore this data pointer. The next, 9. 9 supposed to be
Right.
bigger than 5, bigger than 8, so should go to third one. Even though there's a space here, no. That's 4, less than 5, bigger than 5, less than 8, and bigger than 8 goes to here. Do we have a space?
Yes.
Yes, we have a space. We can just insert 9, 12. The next, 6. I think we missed one thing.
3.
Where's the 3? 7, 3. Fortunately, there's no power. 3. Okay. Then, last one is the 6. 6 is bigger than 5, less than 8. So goes to this one. So we have a space. That's it. And that is the result of this. Check whether this is balanced. Yes, it's balanced.
So it has to be between 6 and 7.
Between 6 and 7 what?
Right.
No, 6 and 7 belongs to this children node. So this children node is pointed by from this. Okay? So whenever you search the data, you need to start from the top. Good to know. Question. What happens if you insert 0 in this index? Why don't you try? I will need 1.5 minutes, 90 seconds. So always first step start with build your node. Okay? Node structure. If you fail to build the node structure, the other will be automatically wrong. Definitely this is the one of the big portion of the final exam. I usually make the question exactly same by changing the couple of value. Good news is the same problem, but bad news is the score. Try. That is the best practice. Okay? I know because you are genius, you understand. You can understand right now, but you cannot solve the problem sometimes, even though you understand the algorithm. The best way is where to try. Practice. So, we try to insert the 0.
Yeah.
How many depth? How many level?
3.
2, 3. How many of you got the 3? Good. How many of you got the 2? Something wrong, I think. Let's see. So, we try to insert the 0. So, you need to first find which node is needed to insert the 0. So 0 is less than 5, so goes to this node. 0 is supposed to be here, but unfortunately, no space
zero.
So 0, that's the red one. 0 is supposed to be here, so it's a full. So in case of full, you need to split. So copy. So we have 0, 1, 3. Which one is the middle way?
1.
So 1. So 1 will be promoted. Okay? Then left hand side, 0. Right hand side, 3. So 3 goes to here. And we need to take care of this. So in order to insert the 0 into parent node, we need a space. Do we have a space? No. That means it's a full condition. In case of full, what is the next step? Just to follow the same step. We need